Hi everyone, and welcome to this short introduction to the Hermans research group. My name is Yves. I grew up in Belgium, where I also studied. My first faculty appointment was at ETH Zurich in Switzerland, and I moved to W Madison in 2014. I have a dual appointment between chemistry and chemical and biological engineering. Main focus of my group is to understand how heterogeneous catalysts work and how we can use those insights to improve either existing technologies or inspire future processes. So you look at catalysis from various angles, which I will show you in a moment. And of course, I'm not always at work, so sometimes I'm also hiking. I also enjoy traveling, woodworking, in and outdoor projects around the house. And I very much appreciate the collaborative nature here at UW-Madison. I get to work with top faculty, colleagues, as well as top students like yourself. This is an overview of the people in my group and where they studied. We're expanding the group at the moment, and about half of them are chemists, the other half are chemical engineers by training. The group works around four pillars, I would say. The first one is making materials and better understanding the materials chemistry. So we use various techniques ranging from hydrothermal salt gel chemistry all the way to the design of multifunctional materials. And we use a large variety of different complementary characterization techniques that are either directly accessible in the group or on campus. For instance, electron microscopy and solid state NMR spectroscopy. Once we made our materials, of course, we need to test them, and we have a large variety of reactors again available, ranging from microfluidic reactors, batch autoclaves, as well as continuous flow reactors. So here you see some either commercially available reactors that we purchased or some home-built trickle-bed reactors. We also use in situ infrared and Raman spectroscopy to understand how the surface of the catalyst looks like, as well as to understand the interactions of reactants and products and intermediates with the surface of the catalyst. And for this, we use, for instance, this trick, which is called modulation excitation spectroscopy, which allows us to filter out noise and signals coming from spectators to better understand what is actually happening at the surface of the material. We also use computational chemistry to predict spectroscopic features as well as reaction pathways, which we can then compare with experimental observations. And an important group goal at the moment is to transform the chemical industry from a linear economy to a circular economy. So instead of producing waste and CO2, can we recycle these two important main waste streams back into the value chain? So recycling plastics and recycling CO2, for instance. Within CBE, we are collaborating with many people, especially currently in the chemical upcycling of plastic, uh, waste plastics center. This is an important topic in the group. We recently published an overview of the existing catalysts. If you're interested in this topic, please contact me. But also outside UW-Madison, we collaborate with people at UCLA, Iowa State, SLAC Stanford, and University of Arizona on either computational projects or advanced synchrotron-based spectroscopy tools, for instance. One project that I would quickly like to share with you is on the oxidative dehydrogenation of alkanes like propane to olefins, like in this case, propylene. So recently we discovered that boron nitride is a very selective catalyst for this transformation, much more selective than the state-of-the-art catalysts reported in the literature. Moreover, the most important byproduct with our new catalyst is no longer CO2, but ethylene in this case, another very important chemical building block. Through a variety of different techniques and collaborations, we learned that what is happening with this boron nitride is not unique, but is a general principle where if you have an amorphous boron oxyhydroxide layer supported on a material, that layer is able to catalyze this desired transformation. And so once we realize this, of course, we're expanding the chemistry now to various other substrates and as well as other chemistries, like for instance, the oxidative cracking of hydrocarbons. So instead of doing a thermal steam cracking or a catalytic cracking, which requires very high temperatures because it's an endothermic reaction. You can do oxidative cracking, which is exothermic. The problem then becomes to avoid the formation of large amounts of CO2. And especially in this system that I show here, this example, we were able to accomplish very stable activities, so long time on stream stability with very low CO2 productivity. I have to acknowledge the support from various organizations, funding organizations, for backing up our research. And with this, I would like to conclude this very short introduction to the group. If you have questions, please feel free to contact me. Thank you.